Neil Lawrence, who will be speaking to us today about deep GPs. So I'm really pleased to be able to introduce him because he's someone who doesn't really need an introduction. No, really. I sort of knew him originally from when I started at Sheffield, where I was leading the machine learning group, which he led for many years. And that's where he started the Gaussian process summer school that's still going strong all these years later. And then after that, he moved to Amazon for a few years before returning to academia and taking up the DeepMind chair at the University of Cambridge. So I'm really glad that he's still like coming back to the Gaussian process summer school every year to make sure we're doing it right. So thank you very much. So this is all about his work on deep Gaussian processes. Cool, thank you very much. Cool, Neil.
Thanks, Mike. So I should add, I'm still a visiting professor in Sheffield as well.
Right, yes, of course, yeah.
And it's nice to see. I'm sad that you can't all be there this year, but actually couldn't have all been there anyway, because there's like 155 of you, and we normally only have a capacity for 70.
Yeah.
Yeah, as thanks to Will, he's put up a link to where you can find notes for this talk. So let me just do some screen sharing. If I can share the right place. So hopefully you see that. And let's just see what Will is.
Yeah, that's that.
Yep. If you also want to find, Will's just provided the link, and the link you're going to is this. When you click on this, it'll take ages to load because there's so much HTML in there. But the other thing you can see as this is loading is there's a link at the top, which is to a Google Colab notebook. I've spent a bit of time this morning trying to make sure that works. So if you want to follow through, those very same notes are also available in a Colab notebook, which will also take time to load. And you can follow through what I'm saying and rerun some of the examples on that notebook. It will load eventually. It's just very big. Great. So I'm going to kill that one actually, because it's just wasting processing. Right. So you actually heard a little bit about deep Gaussian processes already from Carl Henrik, I believe, yesterday.
That's right. Yeah, Carl gave us, yeah, exactly. It's composite GPs.
And yeah, so composite Gaussian processes, yeah, or composite stochastic processes. And I think you also heard something about the sparse approximations to Gaussian processes for making them efficient. So we're going to do a little bit of review of those, but I checked their slides. And so what I'm going to be saying is the same stuff, but in a different way, which I think is one of the things we always try and do on the GPSS. So deep Gaussian processes. Well, the notes, just to say that you'll be using GPy in the examples, plus a piece of software that Andreas Damianu wrote when he was developing deep Gaussian processes as part of his PhD called PyDeepGP. But it's all there for install via Git. Hopefully it should all run on Colab. Okay. So one of the things I like to say is that the universe isn't as Gaussian as we might like it to be. But it once was, as far as I think standard laws of physics understand, fully Gaussian. In fact, I think the standard model of physics suggests it was fully Gaussian, and they keep looking for non-Gaussianity in the early universe to try and find new physics. But at the moment, my understanding is they haven't found it. So this is an image of the cosmic microwave background, which is the moment, I think, when the universe stops being a plasma and condenses, and so light is free to travel. And we can see the echo of that sort of due to rapid inflation. Some of that light is still reaching us. And this is an image of what that light looks like across the sky. And when you study this signal, you find that at that moment, at the moment of the plasma, when it condensed, the universe was a Gaussian process. And the parameters of the covariance function were things like how much matter there was in the universe, I guess how much antimatter, I suppose. I'm making this up a bit because I'm not a physicist. how much dark matter, and so on and so forth. And that kind of dictates the universe we see today. But of course, it is non-Gaussian today. And the reason it's non-Gaussian is at that moment, non-linearities entered the physics in terms of, I guess, asymmetries and all sorts of effects that meant that things sort of condensed in a non-Gaussian way. So the universe we observe today, say our Earth, is actually just a non-linear function of some latent Gaussian process back in the history. So the idea in a deep Gaussian process is, well, if this function is itself a stochastic process, so it could be a Gaussian process, then this would be a function which is a Gaussian process that is a function of a Gaussian process. So the input to the world we see today is given by a function whose input is itself a stochastic process. So this means this is a stochastic process in the end. But if this f is also a stochastic process, we get this idea of composition of stochastic processes, which is the key idea behind a deep Gaussian process. And indeed, we could say this function is itself a deep Gaussian process. So perhaps it's a little bit too simple to assume that all of physics is well represented by one function that is itself a Gaussian process. But it might be conceivable that we could get more complex functions by composing those Gaussian processes together, and that might represent physics. So the argument, what I'm basically saying is, yes, sure, the universe is no longer a Gaussian process, although it once was. You try and find a period when it was a deep neural network. It never was. It once was a Gaussian process, as far as we can tell. And today, you could argue that what we see is a deep Gaussian process. It isn't, of course, but that's how we're going to approximate it. Now, you've heard a little bit about already how we do approximate. One of the challenges in Gaussian processes is the computational demands of the models in their sort of standard form. And you've heard a bit about what I sometimes called sparse Gaussian processes, but a better term is low rank Gaussian processes, because they're not sparse in the strict sense. They're actually low rank approximations to the covariance function. And this always reminds me of this this cartoon that Kai Arulkumuran put together, adapted. So this was, at the time this came out, we were working at Amazon, myself and several people on Gaussian processes, and this reminded me of sort of Amazon meetings and what companies were doing. So people asking for new machine learning projects in the age of hype. And this kind of feels a little bit like where we are in terms of suggesting these new methods. So I feel like this person on the end, oh, let's do sparse Gaussian processes. And yeah, they're not apparently the fashionable things. You feel like you're being turfed out of the window. When you mention such uncool things in companies who have read Wired magazine articles about how AI is changing the world. But actually, there's an enormous number of relations between a sparse or low rank Gaussian process and sort of single layer neural networks, as we'll elucidate a little bit. So you've seen this already. We've got this challenge of complexity being n cubed and storage being n squared. And then we get the low rank Gaussian process. We get to a point where we can have complexity order nm squared and storage order nm. And of course, you may also, I think, have heard about the sort of stochastic variational inference for Gaussian processes, which do slightly better. You get each iteration is sort of order m cubed, and then it's just becoming like stochastic variational inference. So what that's showing is actually we can now run these Gaussian process models at the same type of scale, in theory, as you can neural networks. There are some factors because, of course, their algorithms are very simple. Our algorithms are a bit more complex. So this is the scaling of those algorithms. It's not, you know, there's pre-factors that mean we're still a bit slower and we're not doing billions of data, or the equivalent of GPT-3, where the GP does not stand for Gaussian process. So the approach that we do through this is something that Michalis Titsias worked out when he was in Manchester with the group, which at the time also included Maurizio. And we call it variational compression, and you'll have seen a bit about it in the use of inducing inputs, which can be viewed as sort of pseudodata. So I'm not going to spend too much time introducing that, although my slides aren't advancing. Come on. Because you've seen that by Jen Wen Dai, who was actually just referenced on that previous slide. But the I don't know why my slides are moving slowly. Sorry. It may be just the sharing. Okay. So in your earlier introductions on Gaussian processes, one of the things they may have shown you, and I'm assuming they've shown you in the top of this slide, is that you can go, how you go from parametric models to non-parametric. And what do I mean by this? So one of the beautiful things about, and I think one reason I'm so focused on Gaussian processes, because to me this feels so important, is the non-parametric nature of the model. So if we're in a world where we're absorbing new data over time, and we only have a fixed number of parameters in our model, then what eventually happens is in the standard Bayesian approach, we use Bayes' rule. So here our parameters are W. If you're a statistician, assume this is a beta. Our parameters are W, and our data is some labels and some input if we're doing some regression. And over time, we build up this posterior distribution over our parameters that we obtain from our training data. Now, if we've got a fixed training set, then that's great because we know how much data is here and we spend a bit of time designing our model around how much data we have. But in the real world, you could keep on absorbing more information. And what tends to happen with these posterior distributions, if you have a fixed number of parameters here, they collapse in certainty. So as you absorb more data, if your likelihoods are log concave, then the entropy of the posterior distribution reduces every time you observe a data point, which means it tends to approach something like a delta function. Now, when you're then making predictions on your data, this is the thing that on the left that I always like to highlight, that this object here is the thing we always care about, because this object is the probability of a test label given a test input and all the training data we've observed. And that's the fundamental sort of probability distribution of all predictive work. If we want a predictive probability, we're always trying to construct this joint distribution. Now, people talk a lot about priors and blah, 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 and likelihoods, and apologies for this is a spare bracket, ignore that bracket. But really, what's going on in Bayes, to my mind, is just a way of constructing this distribution. So you have a likelihood of a data point given your parameters and given your input data. And that's the sort of classic likelihood. And then you have a posterior from your training data, which is including all the information about your training data in this parameter vector W. Now, the way you make this prediction is you choose to decompose your probability distribution in this way. We talk a lot about priors and likelihoods, whatever, but this is explicitly what you're saying. You believe that this is true. And what you are explicitly saying is that there is a parameter vector W that is fixed length, that is always sufficient to take all the information from your training data to make a prediction about your test data. Okay, so I paused there to let that settle in. What we're saying is that we believe that there is a parameter vector, W, that is a fixed length, where that length is sufficient to take all the information about the training data and pass it to the test data. Now, if we're working in limited circumstances, that's perhaps a viable idea. It's feasible, but it just makes no sense in general that you could, at the design time of your model, decide what that parameter vector length is going to be. And as you observe more and more data, that's constantly going to be sufficient to be the only thing you need, that fixed length vector, the posterior over it, to represent everything you know about the universe. Now, what's going on in deep learning is, of course, the length of that vector is really, really big. And that's why you're able to use data sets with many billions of values. And so of course, they're going in the same direction of what non-parametric says, that effectively there is no such vector that we can represent this model in, that there is no way of decomposing this joint distribution with a fixed vector in this manner.
Neil,
Yeah,
Just a
go
quick
ahead.
question. Is the bottleneck also applicable in the case of non-independent training data? Like when the likelihood does not factor over the data points?
Yeah, absolutely. That just means if that's a great question, Will. If the likelihood doesn't factor, we're just looking at one data point here. If the likelihood doesn't factor over data points, that just means that when you complete this posterior, you're dealing with non-factorized likelihoods. Okay, it's still, you still have this problem, this decomposition problem, because, and of course you're jointly going to predict, you're going to have to, well, if the likelihood doesn't factorize over data points, then if I've got some of those training data in here, then I'm going to have to include those training data on this side, a few of those training data. If it doesn't factorize, okay, let's step back from that statement. If it doesn't factorize at all, then it's like something like a Gaussian process. And then this doesn't necessarily apply, right? Because you can no longer write this down. But I thought what you meant initially, but as I'm thinking about it, is something like, what if I've got some sort of likelihood where, like a ranking likelihood, so a sort of typical likelihood that doesn't factorize is if there's some relationship between different outputs, so that I might observe, so for example, I might observe two things that are effectively about the same thing. So I might decide that I've got an observation of a person's height that's very noisy, and then I might have another observation that is whether or not someone has classified that person as tall. So I perhaps have the classification, yes, that I think they're tall, and I might have a sense of what tall means. Tall is defined as they're over 6 foot, let's say, or whatever, 1 meter 80 something. But I may also have a noisy observation with a sort of Gaussian variance of what their actual height is. Now, those two observations are no longer independent. So yes, in the extreme case of what you're saying, we basically get non-parametrics, Will. But yeah, if I in the other case where it's just like, oh, there's some relationship between these variables, this is still true. Was that clear?
Yeah, there's a follow-up. Just so the asker. So these aren't my questions. I'm curating from the audience. I don't want to take too much credit. But so in the setting, we're assuming that there's a single true W, which we don't know.
Yeah.
And are there ways then to assume that there are kind of an ensemble of true W's?
Lovely, lovely question. Yeah, it's actually so implicit in Bayesian inference, people even forget it. So when Bayesian inference, you're sort of putting a prior over the parameters that is basically saying, look, there's a single true W. And I only put that prior in once, right? That only appears once. So if I think about what my likelihood typically looks like, I've got a P of W and then a product over the likelihoods, which is n equals 1 to n. Now, that means that what I do is at the start of the whole game, if I'm thinking of the sampling game, I sample one parameter vector, and then I use that vector to sample data points independently, right? But you're entitled to sort of have several parameter vectors, right? And then your parameter starts looking like a latent variable. So we did some work with Magnus Rattray on models that look like this in genomics, where the idea was that you sample a different weight vector for every linear regression, in effect. So every time you want a linear regression, you sample a different weight vector. So, but now it starts looking like a latent variable model, not a sort of standard Bayesian model. So every W, you sample a new W for every single data observation, but it's being sampled from a probability distribution that is not a simple zero mean variance, spherical variance.
Thanks a lot. Oh, yeah, thanks. Great.
But yeah, so I'm assuming in the paradigm that this is one sample of W, right? There is something interesting about latent variable models, about whether you consider them non-parametric or not. They're kind of interestingly non-parametric in a way that's interesting, but perhaps a bit too simple for our needs. But once you go non-parametric, we get this sort of result that I think you've already seen already. And this is what's beautiful. That you get these covariance functions, right? If you assume the Gaussian relation, so if we assume second order only relations between the observed data points. So if we're looking at this system where we say, okay, when I build my joint model over the data, I'm going to assume they're jointly Gaussian, then we can go non-parametric. And within that framework, you can also express parametric models. They end up looking like this degenerate covariance function, which you'll have seen. That if you take a parametric model and express it as a Gaussian process, you get a covariance function like that. And that's why you get these advantages in terms of computation. Okay, so they're most well known as the linear kernel, obviously. Now, in non-parametrics prediction, so I'm moving from y to f. I hope that's okay. But what I see y as is a corrupted version of f. So f is this, I call it the fundamental variable, while y is my observed variable. So you know, for example, in the height example, f is the actual height of the individual, and the two different observations were, one is the observed height with some corruption noise, and the other is a thresholding of the height as to whether they're tall or not. So f to me is somehow a fundamental variable, but they can be corrupted in our observation. What we do in order to make these predictions about new points of the unfundamental variable, it involves combining the training data with the covariance function and potentially a mean function, as you'll already have seen.
Sorry, could you just clarify what was degenerate?
Degenerate is the covariance function. If you have a covariance function that is not full rank, so is not rank n at all times, that's known as the degenerate covariance function. So if you have a parametric model where you've got k parameters in W, then your rank of the covariance matrix will be at most k. And but you could observe more data. So that's a degenerate covariance function. It will be full rank as long as n is less than k, but as soon as n goes over k, and it's that degeneracy that is showing, that is the way this bottleneck problem manifests. Great. So where were we? So parametric is the special case where the conditional prediction of f star given f can be summarized in a fixed number of parameters. So parametric is the special case. It's a massive assumption. Non-parametric is the general case. But the nice thing about that is the complexity of the parametric model remains fixed regardless of the training data set, right? So you have to remember when people are saying, oh, look, the Gaussian processes all these computational problems. Yes, it does, because it's not making this horrific assumption. It's not making a horrific assumption about your data. And if you don't make that horrific assumption, you don't get to do this sort of thing like, oh, well, I can represent the whole world in a fixed number of parameters anymore. And what we're going to do, what I view inducing point methods as doing is reinserting that assumption, but not as an assumption, but as an approximation, right? Which I think is a better thing. And that's why I love those methods, because you're no longer saying this is an assumption. You're saying, I'm going to approximate what's actually going on with a fixed vector. And that turns out to be the inducing vector. So just to highlight that, so what goes on when we introduce inducing variables is we actually augment the variable space. So I'm not going to introduce this notation for Gaussian processes because I'm assuming you've seen it. So what I do is whereas before I had the fundamental variables, f, I like to think of the u as standing for these are the variables that you are going to store about the situation. So f is the fundamentals, the things you care about that's going on in the world. U is what you are going to store about the world. Okay, so you're going to introduce these variables here, and you decide how big u is, and we tend to denote that with m. Now this means we have a joint density, a new joint density. We also have this situation where we don't observe the fundamental variables directly. We observe some corrupted form. And that means that what we actually observe, the joint distribution looks like this, where we're now integrating not over W, integrating over the fundamental variables, where this is a massive big covariance function over F. And just think, Will, one of the questions mentioned, as Will highlighted, the non-independent case, it's covered by this as long as we have fixed clusters of dependencies. It's just simpler to look at the independent case. But what we're saying now does apply, even if it's not fully independent, if there's some dependencies. So in the auxiliary variable approach, we can introduce this new set of variables u. I can write the joint distribution of this in any way. I've chosen to decompose it in this way. But what's kind of fun about decomposing it in this way, I can decompose it in this way. So I've explicitly represented u by introducing it. And now I'm integrating it out. And integrating it out leaves me with this sort of interesting object, which is the probability of y, the actual observations, given what you are choosing to store, what you will keep in your head. no longer given the fundamental variables. Okay, and then what you have is a prior over what you are choosing to store. Now, why this is interesting is because this itself looks incredibly similar to your classic parametric model. So your classic parametric model would say, well, actually, y is going to be some, think of this again as beta if you're a statistician, some beta transpose phi plus some corruption. So we're assuming this is just going to be Gaussian corruption in this case. But of course, in the general case, it could be non-Gaussian, but it would give us headaches when we're doing our linear algebra. So the joint distribution of y is now the integral of the probability of y given w and the prior distribution over w, if we're doing this in a Bayesian way, as we described before.
Neil, sorry, what are the parameters that we're talking about here mainly? Are they like features from the data?
No, the parameters are, they're going to be the weights. This is a sort of generalized linear model setup. So these are basis functions, and the parameters are the weighting of the different basis functions. So these basis functions could be quadratics. So phi, it could be a set of bases, which is 1x, x squared, x cubed. And then the weights would be the sort of polynomial coefficients, yeah? But in general, they could be any set of basis functions. Okay, so very often we would choose a Gaussian prior P of W, and then we've got this likelihood is actually being expressed by this generalized linear model here. This would be the classical statistical setup for a generalized linear model, but not even generalized, just a linear model. And then, as we said before, we've got the bottleneck. But look how similar that is to this. So here the priors over U, what you choosing to store, and here the priors over W, which is also what you are choosing to store because it's the parameters you set. But importantly, U is variables and W is not variables. It's a parameter. Okay. So that's actually what the next slide says. U is not a parameter. So this looks a really cool way because now we seem to be able to compress things in U. But of course, there's no free lunch. You don't get a win here. There's no way you don't suddenly get, oh, so we've solved the problem by just doing a bit of product rule in maths. No, we didn't. No, because what actually happens is P of y given U is itself intractable. That's intractable now. And that's intractable because P of y given U actually is involving all these f's that we've integrated out. And integrating out those f's, there's n of them, is going to give us the same complexity. It's giving us the same complexity as if we just tried to make the prediction directly. So although this object is a very cool and interesting looking object, you haven't won anything here because you've got a load of work to create this object. So the whole idea to me in inducing variables is that you actually approximate that object. So what you do is you build a variational bound on P of y given U. And you see these variational lower bounds. I've seen Carl Henrich's slides, did a nice job on doing Jensen's inequality on them. And what you do is, in effect, you say, okay, well, I'm going to, instead of computing this thing exactly, which is the integral over f, which is tractable, but it's going to give you all those complexities in n. Then you choose to variationally approximate it. And that's the core idea behind Michaelis's paper that he wrote when the bulk of the group was in Manchester, including Carl Henrich and Maurizio and others. So that's kind of what happens. I'm not going to go through the details of that because I want to get onto deep GPs, but this trick is at the heart of deep GPs. So this trick is what enables the approximations tool work for deep GPs downstream. I mean, it's a sort of beautiful trick that enables 1,000 things. And the reason it enables those things is because it's starting to get your what was a intractable non-parametric model to be a parametric approximation, something that looks like a parametric model. It's not a parametric model. It's a non-parametric model, but it's something that has the form of a parametric model that is an approximation to the non-parametric.
Neil, could you just, what's the benefit of U being a variable then rather than a parameter?
Okay, so the most beautiful benefit of that is that I can change the size of that vector at runtime. And what I mean by runtime is, I mean, once I've decided what my model is, there's nothing to stop me changing the dimensionality of U while I'm in the middle of absorbing data. So I can have my model, I can absorb 1,000 data points from the world and be making predictions by setting U to 100. And then I might think, oh crap, U is looking a bit small. It's not big enough for me to represent what's going on in the world anymore. Let me expand U to 200. Yeah. And I carry on. And because this is an approximation to the non-parametric truth, where truth isn't real truth, it's a modeling truth, I can get away with that. It's still a lower bound. It's just a tighter lower bound. By increasing U, I can't reduce the quality of the bound. I can only increase the quality of the bound. So I can make decisions about how much compute and how much I want to store about the data I'm seeing live while the data is coming in. Now that seems less, I mean, it's not apparent why that's useful. If the whole world is about training, I'm going to train, I finish training, I never look at my model again, I then use the model in practice. But that's not how the world is. I mean, the world is a dynamic, moving place where you're absorbing new information the whole time. So that's massively important. And I think no one, well, very few people seem to get that point. They just look at the maths and go, oh, oh. But I think that's because they don't think about what it would mean to be running a model in practice. Like what you would have to do in a parametric model is sort of add in new parameters, and you'd have to think of some heuristic way of dealing with those new parameters. I tell you, there's a model that sort of does that. That's called it's called the RVM star by Joaquin Quinero Candela and Carl Rasmussen. It sort of introduces a new parameter every time there's an observation, and it does that in an effort to try and get good error bars for a fixed basis function model, but it leads to a lot of headaches. So this is a cleaner way of doing that. Okay, so I'm not going to say too much more about that, because what I wanted to do there was just highlight that these models are giving us an ability to, I actually had a nice thing here. Oh, they're like pseudodata, these U variables. You can do all sorts of imaginative things by them. And this is a totally unexplored area. Sorry, everything's going very slow. I'm not actually clicking. It's just moving of its own accord. Right. What I wanted to say there was that in particular, when you've got this representation, you can all of a sudden apply this beautiful idea from Matt Hoffman, David Bly, and others called stochastic variational inference. So that's the sort of Gaussian processes for big data paper that we wrote with James Hensman and Nicola Fusi in Sheffield. And that's a massive thing. Like, I mean, everything kind of is going to stem from that. And it is stemming from that notion that you can combine this inducing variable. Well, the inducing variable idea isn't originally due to Michaelis, but he noticed that there's a variational interpretation. But this variational interpretation of the inducing variables, this nice idea of stochastic variational inference from the sort of team at Columbia, and then you get stochastic variational inference for Gaussian processes, and all of a sudden you can do things at enormous scale. And then like there's a host of papers saying, oh look, we could do this and we could do that. But those are the key ingredients. So the sort of principal ideas, principal component ideas behind what's going on now. So, and that's sort of super important. And it was this year, sort of 2013, when James was doing that in the lab, was also the year when we were working on Gaussian processes. So everything sort of comes together. So there's some examples about how these inducing variables work in the notebook that actually comes, I think, from an original set of examples by James that I've recreated. And you can play with those to try and get a sense of what inducing variables are doing. Since then, Tang Bui and Rich Taylor and others have written a beautiful paper that I recommend everyone reads that sort of also looks at these frameworks for pseudo-point approximations or inducing variable approximations, and shows that there's a sort of a relationship between other approximations, these FITSI approximations, and explains what that relationship is. And we're not going to talk about that any further, although one could do, and Rich has in the past. You can find videos of him at the GPSS talking about that. And we're going in this direction. Andreas Damiano, who is a PhD student in Sheffield, with me, who worked on one of the ideas that stems out of all this maths, which is deep Gaussian processes. So we're at half an hour or a little bit over. Let me just pause there and check again if there's questions before we move on to the deep Gaussian processes. And I may even stop sharing screen for a moment so you can see.
Yeah, so there's one question on deep GPs. I'm going to save that for later when you've actually introduced them.
Yeah.
And then the other question is could you use this kind of approach for modeling time-dependent distributions, such as diffusion in physics?
So modeling what dependent distributions?
Time-dependent distributions.
Oh, yes, right. Yeah, no, that's really, oh, wow. Wow, it's hot today with the questions. Yeah, time, you can use them, but they're kind of limited for that. And actually, Rich Turner's worked on this quite a bit. Why are they limited? Because we don't, so these time-independent things aren't really low rank. There's a number of ways. Okay, so I get made fun of for saying this, but I'll say this and again. I mean, most things that a lot of people are doing can be viewed as a Gaussian process, right? But they are different ways of making the Gaussian process efficient. And things like Kalman filters are just Gaussian processes. But the reason they're efficient is because you're exploiting the sparse structure in the inverse covariance of the Gaussian process. Okay? The standard parametric generalized linear models are also Gaussian processes if the likelihood is Gaussian. But the reason they're efficient is because the covariance is naturally low rank because it's degenerate. Yeah. So you can try and use these inducing variable methods for time, but the interesting structure in time is actually the sparse inverse. So the inverse covariance function, the precision matrix, is sparse because it's representing conditional independencies. And these diffusion processes often had sort of Markov properties in them so that they have limited dependence over time. And that's the property everyone's exploiting when they fit diffusion processes. Now, there's really great work by Arno Solin and Simo Saka in how you convert Gaussian processes to those structures and fit them extremely efficiently. The challenge is making these two approaches compatible. So this is great because we can do time efficiently, we can do spatial processes efficiently. But what you really care about, and if we could do, my goodness, if we could do large scale efficient approximations to temporal-spatial Gaussian processes. I mean, what do you think is going on with COVID right at this moment? That would be a latent function for estimating R. If you could do that efficiently, you could get really great estimates of COVID on a local region. But people don't. They keep it separable. They do the time separately from the spatial. And the reason they do that is because there are nice approximate methods for time and there are nice approximate methods for spatial, and they're not necessarily compatible. Other questions, or shall we push on?
I mean, unless anybody urgently has a question. Do I get the same result if I start out with m inducing points and then add 1, as opposed to starting out with m plus 1?
Ooh, if I start out with n and add 1, so n is the data set size. And
no, so starting out with m,
yeah,
and then adding 1, as opposed to starting out with m plus 1.
Oh, well, that's a good question. It's going to depend how you introduce the inducing variables, because now you've got an optimization problem for these inducing variables. So in theory, you can get the same result, but in practice, you're probably going to have a bunch of heuristics for how you choose to introduce and optimize the new inducing variable, where you may not want to optimize all the previous inducing variables. Yeah. So the math says, yeah, well, it's the same. You've got the same representative power as long as the nature of the inducing variable is the same. But in practice, the reason you're probably doing this is because you're going to be having a bunch of heuristics you're trying to you're going to have a bunch of heuristics that you're trying to use to make your whole system run efficiently. And probably those heuristics mean that you don't find the absolute best solution for the inducing variables. You just find a better solution than you would have done. And I think the one thing that depresses me a bit is we're not at the stage with Gaussian processes where it's easy for people to try out their heuristic ideas for how to introduce new inducing variables. And that's one thing that's limiting our ability to deploy these things at scale. And I'm, okay, maybe some of that's going on when people are using for Gaussian processes for machine learning type tasks, like I'm trying to use a Gaussian process to recognize ImageNet or something. But actually, I think the more interesting domain is when you're trying to use a Gaussian process for all these more traditional tasks, like I'm trying to estimate the amount of COVID across the UK, or I'm trying to estimate the amount of malaria in Uganda or something like that. Which is, I mean, those models are far more widespread than people give credit for, just because we don't talk about them at Europe's, I guess. Okay, I better move on just because otherwise I'm not going to get through it. Get on to detail.
Yeah, I was going to say at the end, maybe a few people are asking for different references. So at the end, just direct to references. All right, let's carry on then.
Great. Let me share screen again. Okay, so this thing, you know, when I joined machine learning community back in 1996, I used to see talks about Gaussian processes, and they would blow my mind because I was at Aston, where Chris Williams is, who's being cited in this paper by David Mackay. And this is a quote from David Mackay gave a Europe's tutorial in 1997 on Gaussian processes that I went to, and I didn't understand Gaussian processes, but they blew my mind. I mean, everything they were capable of doing at the time I was working on Bayesian neural networks, or trying to, or starting to. And the capability of these models to do the things that we were desperate to do with these neural networks that I was working, it just, to be honest, it totally blew my mind. So David gave this talk, which kind of, I knew about these models and I was already interested, but kind of blew my mind. And then at the end, he said this thing, well, have we thrown out the baby with the bathwater? And what he sort of says is, Gaussian processes, so neural networks are supposed to be intelligent models that discovered features and patterns in data. Bear in mind, this is 1997, right? So you can see how little is new in terms of what people are saying about neural networks, because people have been saying that since 1987, as he is saying here. Gaussian processes are, in contrast, simple smoothing devices. How can GPs possibly replace neural networks? What's going on? And I think the answer, and this is what David's hinting at, is that, you know, they're not doing everything that, say, a layered neural network does. And we'll see some of that coming up. In particular, this point about them being smoothing processes is something that is very obvious and is a limitation of the Gaussian process formalism. And one of the things we're going to see when we introduce deep Gaussian processes is that, and one of the things I really like about them, because it shows, well, something really different is going on, is that they allow non-parametric discontinuity. Now, why do I say non-parametric discontinuity? Well, because I can easily introduce discontinuity in my Gaussian process. That's no problem. I can just say, I can introduce a single basis function, the mean function, which is a step. I can put a Gaussian prior over the location of that mean function. I can say at some point, there's a threshold across which the processes become independent. That's fine. But every time I do that, I have to introduce a parameter to represent that discontinuity. Pausing again to let that sink in. So what I have to do, if I'm going to do that, is I have to say there's going to be a discontinuity at time capital, or time tau, right? And I have to then introduce, I end up with a tau in my covariance function, and I maximize the likelihood with respect to tau. It's great, but it means a priori, I have to know how many times they're going to be in the system. So I'm back in this world of a fixed parameter vector, how many discontinuities there are going to be in the system. So if we take something like the financial markets, that's like saying, before I model the financial markets from now until the end of time, I'm going to know how many crashes there are in the financial markets, because I have to have a parameter for every crash. Doesn't make sense. The non-parametric processes that allow for jumps is a set of processes called sort of Markov jump processes. I mean, well, ones that are tractable that we can use. And if you combine Markov jump processes with Gaussian processes, if you add them together, you get something called a Levy process that allows for both. So why aren't we using Levy processes? Well, Levy processes, apart from the specific case where they are Gaussian processes or Markov jump processes, they are intractable. You can't, right, well, you can't write down the likelihood in closed form. You can only represent them in terms of their characteristic function. So deep Gaussian processes are an attempt to get some of those characteristics. Again, they're not tractable. We can't write down their likelihood, but it turns out we can approximate their likelihood. We can lower bound their likelihood. And that's a major motivation for stochastic process composition. So it's coming really from David, Europe's tutorial 1997. You know, the guy blew my mind and then said, oh, and there's a limitation. Okay. So deep Gaussian processes try and address that limitation. So let's look at deep neural networks, which is the sort of thing, and this is just a fully connected deep neural network. And I've put the inputs at the bottom, which is which upsets Yoshua Bengio. First time I did it, I didn't know that that was against standard, but once it upset Yoshua, I like to tease Yoshua, so I do it all the time. So here's the inputs to the neural network at the bottom. So this is often some image or something like this. In a fully connected model, there would be a load of convolutional layers if it was an image, but then they're just going through, well, let's get the maths up. What you can see is what's going on is that what's going on at H is you have a set of activation functions. So you have X at the bottom and you multiply X by a matrix W. So if we're looking at H1, the sort of lowest row on the screens, let me just show you there. We've got H is given by a set of activation functions. So I'm thinking of them as basis functions, but these would be ReLUs, rectified linear units in neural network parlance. But they're just simple basis functions that we can build Gaussian processes out of as well. And the input is X, and that's being multiplied by a matrix W to give us the entry to the activation function. And the output of these activation functions, H, is a non-linearity around those inputs. And then what we do is we feed that output into a set of inputs to the next layer. So instead of the next layer taking input as X, it takes an input as H1. And we just do this one row after another till we get an output. And I'm doing a regression model. So my output is just a linear weighted sum of these basis functions. So the standard model I was showing you before would just be this layer here plus this layer plus a set of inputs, right? So these top three things, that's the model I was talking about before. Okay, so this is what's going on mathematically. And the reason that the number of parameters goes up so quickly in a neural network is because each of these matrices W is the size of the hidden layers. So they use very large. So if I have 1,000 hidden nodes in this layer and 1,000 hidden nodes in this layer, this matrix here, W, is 1,000 by 1,000, so it's 1,000,000. And they do use, you know, dimensionality of 1,000 in these places. So they start getting an enormous number of parameters very quickly. And they kind of want that because they've got the same, you know, I don't think they view it this way, but from a modeling perspective, they want that because they've got the same challenge we have with the non-parametrics. And they're kind of solving that. They're solving that in a very interesting way. They're saying we're just going to have an enormous number of parameters, way more parameters than we need. And then this whole problem I talked about before effectively doesn't come up. But that's odd because you need some sort of regularization. And there's all sorts of really, really interesting work around how these models are regularizing and how they're fitting, and this concept known as double descent. And if you're interested in that, I urge you to look at it. But actually, one of the things it turns out that these models do is when they are fitting well to and generalizing well, that turns out that these matrices W tend to be low rank, right? So it turns out that the effective number of parameters the model uses when it has a good fit is not the full rank of the matrix W. And so what does that mean? That means that in effect, you can parameterize the solution with the single value decomposition, where you're setting lambda to be much less than K1 and K2, where those are the size of the hidden layers. So you can sort of set, that's the single value decomposition, but you can conceptually just combine the square root of lambda either side and just write it as a U times a V. And the reason I like to write it like that is because you can see how the matrix is being generated. So I've colored these matrices these are actual numbers, but I've colored them to give you an idea of, it's just a low rank approximation to W, which is not a symmetric matrix. So you need two matrices. The type of low rank approximations that come up in sparse GPs are using KUF, the covariance between U and F, to generate this thing, and they generate symmetric matrices. But here we don't. But of course, one of the funny things about neural networks is, and this was true in the 1980s and early 90s, and it's true again now, is the way that people ignore the fact that it's linear algebra underlying it. And then they talk about bottleneck layers. So one of the things they'll say in neural network parlance is, oh, let me introduce a bottleneck layer. And a bottleneck layer is the same as one of these layers, but the activation function is linear. So it's like, I'm going to have a linear neural network. But that is effectively, that turns out to be just this. So it's a sort of low rank constraint. So when you're introducing bottleneck layers, you're placing a constraint on your deep neural network that is basically, you've got a low rank matrix here. And by the way, I also learned this trick in David Mackay's group meetings back in 1998 in Cambridge in the Cavendish lab. So we can actually write the mass for what we're doing now in this way. So if we've substituted UV in for W, we can rewrite the mass and introduce this new variable Z. So Z is now V transpose H. H is U transpose Z. And so the sort of V is appearing in there if we substitute this term into here, and then we recover what we had before. We've got the low rank approximation in. Now, mathematically, that can be written in this form. So by the way, this formulation I talked about in 2013-14, and I'm staggered by how slow people have been to dawn on them that how close this makes deep neural networks and deep Gaussian processes together. And more recently, a lot of papers have, I think, twigged on the same thing and started talking about the relations using these formalisms. I guess we made the mistake of never writing a paper that talked about this, but it seemed so obvious to me that it didn't seem worth writing a paper about. There you go, stupid me. So the network can be written mathematically in this form now. And this is interesting because if I look at any of these particular parts here, this Z being multiplied by V on H, and then going into here and coming out to a set of variables Z, this little triplet here is a generalized linear model on its own, of the classic type that's used in statistics. And if I take, it's going to be next slide, I suspect. So I can view this as a cascade of neural networks where I have this sort of odd starting point where I take my inputs and I multiply them by a matrix, but that matrix could be identity if you don't like that. And then I start going through a series of neural networks, and then at the end I take the output and I multiply it, because I want just a unidimensional output, by a vector. But I can combine W4 and V3 if you don't like that. So what you're seeing is that a deep neural network, if I introduce these bottlenecks, is just a cascade of single layer neural networks. Pausing there. And we already knew back in the day, and it's in Mackay's tutorial and everything else, that Gaussian processes have an interpretation as neural networks where I take the number of basis functions in the hidden layer of the neural network, or some of neurons, as they would say, to infinity, which is why I was so into them. I was like, why am I messing around with these neural networks when I can have an infinite width neural network? Because at the time, in the sort of 1990s, we were mainly working with single layer. And I could just go for the Gaussian process directly and get all these sort of advantages of non-parametric nature. So the deep Gaussian process is just the same idea. So instead of that, look, we'll just replace each neural network with a Gaussian process. And therefore, well, I don't want to go through those deep learning slides because I think probably I've got time.
You referenced the tutorial. Yeah, whose tutorial was it? Sorry.
David Mackay's. So it's in my citations at the end of the slides. So you can either get the slides online, where you'll see these citations are at the end of those notes. In fact, let's just Let's just review that because those things will have come up now. So if you clicked on the collab, you should be getting, with a bit of ugliness that I haven't sorted out because these slides were auto-generated. And this is like for just downloading all the bits of software you need to run the examples. You'll see me saying in text with citations to the papers, pretty much what I'm saying here now. For some reason, I don't know why, but for some reason, if I use Pandoc as I'm using, some of the citations, the year doesn't come out. But hopefully, I haven't double checked this, hopefully at the bottom, we should find, okay. So for some reason, Colab likes to hide cells. So you just have to click on them. And I don't know why it's chosen to hide. Right, so this is where we've just got to, right? So this is what you're about to see coming up, although I'm going to skip this section. Hopefully at the bottom of these slides, because it's a long way down, you should find references. Oh, hidden. Yeah. Yeah, see all that. Okay. Other questions at this point before I skip the next section?
Yeah, there's a question. So in practice, in cases where data dimension is high, is it good to do like having a deep kernel rather than a plain GP? And
yeah, it can be. It's a major motivation, actually.
The bottleneck neural network.
Yeah, great question. Yeah, whoever asked that, 12 points. Yeah, because one of the motivations for why you might want to be doing this is kind of, I mean, the curse of dimensionality is a crock. It never exists, right? It never exists in real data. I mean, it exists mathematically, obviously. But the simplifying assumptions you make, like that all your features are going to be independent and all your data points are going to be independent, if that's true, we call that noise. Yeah, pause on that. If your features are independent and your data points are independent, you've got noise. Now, we definitely know that noise exists, and normally we're using, I mean, whether it exists with that level of independence, I'm not quite sure, but we're using that type of term to mop up the bits of the model we don't care about. So yeah, in high dimensional data, the sort of thing intuitively, the two things could be going on where the structure, which kind of relate quite closely to what we just said before. You're either going to have conditional independencies in that high dimensional space. And that's the sort of thing that people try and address with graphical models. So you've got some high dimensional data, but it's not, but there are some conditional independencies, like in a time series. Time series is very, very high dimensional because time's infinite, but the structure is that you've got dependencies between different time points. And, you know, that's one way of dealing with it. The other one is kind of the manifold assumption that you believe that while the data is high dimensional, there's some true underlying, and mathematicians hate that type of term, so you have to be careful, but there's some embedded manifold where the data is sitting, which is of lower dimensionality, right? And it likely fills the space because there's a bit of noise. And when you're building a model like this, you can argue that what you're doing is, let's say this is 1,000 dimensional inputs, you can argue that you're projecting it down to 4-dimensional inputs. And when you're doing it at this layer here, you're going 1,000, ignore this bottleneck, let's just look at this bottleneck. You're basically saying, I've got a nonlinear function mapping myself down to 4 dimensions, and then I'm going to fit in that space. That's a very, very sensible approach to high dimensional data. And when you do it with the Gaussian process, you're doing it non-parametrically. And for me, that was another major motivation for these type of models. Other questions at that point?
Nothing specific, so you just move on.
Cool. Okay, I'm going to skip this, which is like a little bit of a deep learning motivation. But apart from just to sort of say, because I'll have these plots later, that you can think of deep learning as, oh, bloody hell. And click and be patient. Deep learning is a bit like pinball. So what do I mean by that? Well, imagine I've got 1-dimensional input. So this is my X, and then my dimension on this space is 1-dimensional. So this is all going to be 1-dimensional, a bit boring. I'm going to have a bottleneck layer going down to a 1-dimensional output, right? So So what conceptually, each of these gaps in the pins is going to be a one-dimensional output from my previous bottleneck layer, where I've got a sort of neural network in between, right? So I like to describe things like this because everyone says, oh, it's magical and you can't understand deep learning. But really, you know, this is kind of all that's going on. And then, of course, here I'm thresholding the output because I'm classifying. And of course, the start point here causes the ball to fall in a certain way. By the way, I've tried simulating this and I can't get a pinball machine to actually look like this, but you know, conceptually. And then the idea is that the fitting of these models, these deep neural network models, is the movement of the parameters, which in their case involves moving the basis functions around. So they end up in each layer moving the weights to change the location of these basis functions, which in my case are pins. And of course, we're bottlenecking here at each layer. So they don't tend to do that, right? Because they stay high dimensional when they get between these layers. But conceptually, you can think of a bit like that. But of course, what's going on really is it's not a one-dimensional input. It's a massively high dimensional input. Like it's an image with millions of dimensions. And then it's going through this set of basis functions that you can't think of as pins. The pin is like, if it's a ReLU, what is the hinge point of the ReLU? But you can think of them as sort of high dimensional planes, hyperplanes. So it's like, so deep learning is like playing pinball in hyperspace, I kind of think, where you've got this cascading effect going on. But that's not what you must say to mathematicians. Do not say that, because what you can say is it's a composite multivariate function, which is basically what it is. It's a composite multivariate function. And then you might say, so any mathematician will look at that and say, well, what's the point of that? Why don't I just write down G? Well, the point in that is that I can get a very complex function G by composing simpler units. Yeah. Now, in the neural network case, the trick is all the these simpler units are differentiable and have these particular computable properties that I can put through a GPU, give Jensen Huang enough money to buy the most important semiconductor company in the United Kingdom, because he's got a simplistic enough processor that does this computation very, very well. It's a bit depressing, that, isn't it? Whereas in the Gaussian process case, what I care about is that I can put uncertainty in each of these layers. So there's two sort of things going on. There's a related reason why we like the composite multivariate nature. One is that I've got these units where I can do automatic differentiation. I can do the chain rule to propagate it through the multivariate function. I can do my fitting in that way, and I can get a more complex class of functions I'm fitting that I can compute relatively efficiently. But in the Gaussian process case, it's like, well, look, if these are stochastic processes, this is a crazy stochastic process that I can't compute analytically. But if I have approximations that allow me to compose these stochastic processes together, I get some very interesting structure in my final stochastic process. So it's a much richer idea, I would claim, obviously, much, much richer. It has all the facets of deep learning, plus it's got, well, I'm going to push uncertainty through this thing. And therefore, I'm going to get some funky uncertainty out on the far side. And its disadvantages, of course, is algorithmically, it's a lot harder to do. So that's why we struggle to sort of scale to the size of data sets that those neural net people can do. I mean, I should pause and say something briefly about Bayesian neural networks, because I worked on Bayesian neural networks back in the 1990s. I'm not ruling out the idea that Bayesian neural networks end up offering us something useful, that we get there through them. But the errors they're falling into in that space that we established were problems in the 1990s, and they keep on hiding what's going on, are astronomical. Because the main problem is this. It's a different approach, right? In the Gaussian process approach, you say, wow, look at my wonderful uncertainties. I care about them. I'm not going to throw them out with the bathwater. I'm going to keep them and compose the uncertainty together. The neural network, Bayesian neural network approach is more like, oh, I'm going to throw out that uncertainty, try and use these nice algorithms and reinsert it later. And that has problems. And most of the problems are around how you're reinserting that uncertainty and whether it gives you the nice effects. And we'll see an example of that later. And one thing you really have to look at when you look at papers from Bayesian neural networks is not just the quality of their error bars, which are often shocking, but also when the error bars are good, the quality of the fit, because what tends to happen is when the error bars become good, the fit becomes shocking. And in Gaussian processes, you don't tend to see that. And you can see that Gaussian processes are still the dominant formalism because they keep inventing new methods and they keep comparing to Gaussian processes, right? So if there was a dominant formalism that was doing the same thing that GPs can do, they would compare to that. There isn't. They keep comparing to Gaussian processes at the baseline, saying they've beaten them. And you can tell that they're not doing better because there's no sort of new thing. I mean, certainly they create some very interesting models, and I'm not saying dismiss it all, but basically the hype is well in excess of what has been produced, which I think is not leagues ahead of where we were 20 years ago. Okay, so after that little rant,
Neil, are you saying that if the influence of the prior will rapidly decrease in a deep GP, and would you consider that an advantage or disadvantage?
If the influence of the prior would rapidly decrease in a deep GP, you mean the prior as a Gaussian process prior?
I guess, yeah.
That's kind of not what happens, and people keep assuming that that's what happens. What this does is actually create a much more structured prior. So oddly, a Gaussian process prior is one that, as we know, it's a universal function. It can fit anything. It's just there's a bunch of interesting functions it doesn't like to fit. So what actually is happening in these things, and you have to think about it quite carefully, is the space of functions that this starts to support will, for certain parameterizations, I should say, if you don't change the parameters, is a sort of more restricted space of functions under the prior, but some of them can be things like they have discontinuities in them. Yeah. So be careful. This doesn't you can't sort of it's a bit hard to sort of conceive, but when you're composing probability, maybe it's easier to conceive when you see it this way. There's sort of a product of probability distributions going on, right? If you put something down in this probability distribution, when you're weighting it by these other probability distributions, if they're log concave, this final product of probability distributions has lower entropy than this starting point, right? Which is what they tend to be, I think. I mean, would that be right? It's not universally true. It's not always going to be true, but often that's going to be the case. That can't be universally true, because these are quite complex, because each of these is a Gaussian process, or what I would say is a GPLVM. So I think that people get the wrong idea when they see this and think that the prior is becoming more diffuse. I think it's just changing. It's not even becoming more concentrated necessarily. It's just changing, and it could be becoming more concentrated, I guess. Sorry, that probably wasn't a great answer. But structurally, as probability distributions, we can write them down like there's this chain. And this is the way we would have thought of it in the days where graphical models were popular, that actually all you're doing here is writing down a chained relation where each of these distributions itself is a Gaussian process. Now, the reason I write it like that to form the deep GP is to sort of highlight that this is the least interesting thing you can do with a deep GP, right? So if we put it around that way to make it like a deep GP, and here to keep Joshua happy, we put the X's back at the top. I've talked about that actually, but it's in there in case I forgot to. I'm talking about this new way of, but what I really wanted to sort of highlight, if it is on my next slide, is this. I mean, it's the simplest thing I might imagine doing. Here, I've said, okay, I'm going to have a side observation from somewhere up the top. And I'll have a slide at the end, if I get there, to sort of show what I kind of think of this means. So here I've got one observation Y, which is going through the whole deep Gaussian process. But then I've got some side observation, Y2, which is hanging off the side. Because to me, this is the sort of structure you want to get the worlds of. So there's a sort of world out there which combines all the advantage of graphical models where we're putting in those conditional independencies. So this is hinting back at the conditional independent structure. So inside here, we've got the low rank structure. You can't see that anymore because the new way I've represented it. But we're also sort of saying, look, there's some sort of conditional independent structure. And here we're saying, well, this Y2 is based on earlier latent variables coming from X than this Y is. So we're saying something about the probabilistic relationship between these two things. And, you know, it's remarkable, not that we've done enormous, because actually I do like deep GP still, but I really just enjoy it when other people work on them and come up with creative things on them. And I'm kind of hoping people do things like this. One area where you see this being done is like multi-fidelity learning in uncertainty quantification. There's quite a lot of work emerging on that, including work from people who've attended the Gaussian process summer school in the past. But this is a bit of a nightmare, because what happens is if we're saying that we've got some X, and then I'm going to put it through a Gaussian process as I've done here to some Y. So I've got 2-dimensional X, I'm going to a 3-dimensional Y. When I've put it through this nonlinearity, and actually there's another paper, David Mackay's, which was the first paper I saw to do this sort of thing, called density networks. If I put it through this nonlinearity, if I've got a Gaussian distribution in this grid here, it becomes non-Gaussian in this space, and that becomes intractable. And that's the sort of challenge. This is why these things are intractable. Here's another image to try and highlight that. This is in the 1D case. So this is like the pinball case, one layer of pinball. If I drop the ball in at the top layer, and then I put it through a Gaussian process to see the position of the ball at the next layer. So this is the location along the x-axis, and this is the location along the x-axis, even though it's P of y, the next layer. Then with just a sort of nonlinear function here, this becomes massively multimodal and complex. So this already, I mean, and this is kind of a little bit what's going on with GANs and all these generative models. You've got a Gaussian that you map through a nonlinear function. And if this is a non-parametric function, I've already got a non-parametric probability distribution. And the point in deep Gaussian processes, you're going to do that multiple times. So just quickly to try and show what one has to do is, and this is why I sort of reviewed the low rank Gaussian process approximations, because if I try and deal with this, I get a variational approach. So here my Z is my input to the Gaussian process, because that's what was going on in the hidden layers. And P of y given Z is my full covariance Gaussian process. And if I want to try and say, well, I put a prior over Z, then here's the prior. I can build this variational lower bound using Jensen's inequality. This is the standard variational thing I might try and do. But it fails because when I write out that likelihood, so bear in mind the likelihood here, P of y given Z, is we're going to need a log of that and the expectation of that under Q of Z, which will typically may assume to be a Gaussian. So we'll make an assumption about Q of Z. Gaussian would be a standard one. And when we do that, let's look at what log y P of y given Z is. Well, it's the classic quadratic form of the Gaussian process that you all know and love now after 3 days, or maybe you're sick of it, but it's the most wonderful thing. And it involves X is appearing inside this KFF, but worse than that, X is appearing inside KFF after an inverse. So if this was just, if each element of this matrix K was just a function of two pairs of X, that might be fine. But once the inverse happens, the X's get distributed across this whole matrix, and the expectation becomes extremely difficult to compute. So that's why the standard variational approach fails. But when we go for the collapse bound, and remember I said the beauty of the collapse bound is it makes everything start looking like a parametric model again. One way of writing that collapse bound, which I didn't get up to, but it's in other papers, is here's a new likelihood where this is the expectation of F as expanded out here under this conditional distribution. So here, this looks like a likelihood of our data, Y, given this expectation of F, a Gaussian noise, and a prior over U. Now, it turns out that that expectation of F, because it's just a Gaussian process, is, perhaps I don't show that. Okay, I don't show that. But this expectation of F is linear in U. That's the important bit, okay? Because it's the mean of a Gaussian process, right? Because this is a posterior of a Gaussian process. So it's linear in U. So it's easy to deal with. So this whole likelihood on the left is linear in U. So what I do is, okay, now I quickly, don't integrate, stop. Don't do the integration. Introduce Z and now integrate over Z first. Ha ha ha. So now if I introduce the Z that I want to get rid of, I can now do the variational lower bound. And I'm not going to go through the details. It's sort of in the notes, but I can do that variational lower bound and a number of terms come out. And that's why the inducing variable trick is so important. Now, when we do it, and certainly when we did it originally with Andreas, and also, I mean, Michalis would have been fully aware of this. He was definitely involved. What turns out is you need these expectations of the covariance function. These all turn out to be computable, and we call these the psi statistics. And we did them analytically in the early days, but nowadays people do a lot. They're doing them through these sort of doubly stochastic methods that Michalis, I think, is also one of the proponents of, through sampling these. And Andreas did suggest that in his thesis, but he didn't go deeply into it. But Hugh Salimbaini and Mark Deisenroth had a lovely paper on that. That makes these methods that you don't even need to do this analytically. You can just put any covariance function in there you like, which is quite nice. I'm rushing through a little bit to make sure I get to some of the examples. There's other approaches as well. So actually, I worked on these models way earlier with a guy called Andy Moore. There's two famous Andy Moores that aren't him. Maybe he's famous another way, but two famous academic Andy Moores who he is not. And then people have looked at it with Hamiltonian Monte Carlo and expectation propagation. That's Tang Bui, who does a lot in this space, with I think Miguel Hernandez Lobato and I think maybe Rich Turner. But just to highlight something, because I said this before, and this is taken from this paper, and I mean, no, I don't know. It just makes me a little bit cross. Sorry. This is a fit where people are sort of saying, I can't even remember which their method is, but just look so carefully at these fits. This is a Gaussian process fit. Notice something about the Gaussian process fit. The functions go beautifully through where the data is, right? Very tightly around the data. This is, I think, the sort of standard method that isn't doing the new thing in this paper. And this is the standard weakness of these standard methods, is that what they tend to do is they don't go high variance outside where the data is. Okay, so this would be a Bayesian neural network approximation. And everyone freaks out about that, right? And they say, oh, I need new methods. I'm going to have new methods. And they're so obsessed with getting these error bars up here that it seems to me that they don't even notice that the model has stopped fitting the data. So this is a really, really important point. These error bars, you gain nothing in your likelihood for getting them right. Pretty much nothing, right? So that when you're doing a variational approach, it's all about optimizing the lower bound and getting a tighter lower bound. And you sort of might think, well, if I get the error bars right, I will get a tighter lower bound. You will slightly, but why do you gain nothing? Because they're arising from the KL divergence term. They're arising from the fact that the KL divergence between the prior and the posterior, as soon as you leave the region where there's data, everything is dictated by the prior. But that term is very non-influential in the whole thing. It's a small term. The amount you score is very small because it's of the scale of one data point. So getting these error bars right, always remember this intuition. Just think about what you're doing and remember this intuition. Getting these error bars right is equivalent to, at best, getting one data point right. Something like that. Order that in information theory terms. Yet these approximations, what you can see they all do in order to get better error bars here is they destroy the fit where the data is. And pretty much the only thing you know about calibrated error bars is what those error bars should be in regions where you've seen data, right? Everything else is your prior. And you see this error again and again with these Bayesian neural networks, and reviewers don't pick it up. And it bugs the hell out of me that, yes, we would love to get these error bars right, but please look at what's going on in the region of the data when you've modified your method. I mean, look at this one here, where we've got error bars that are way above where they should be in the region of the data and way below. And what you'll see if you can zoom in, which you can't in this case, is that the mean function has started stopping fitting. I mean, this is also what's happening here. This is the most chronic case, but I think that this is this isn't an example that's being proposed. But every single case, apart from the Gaussian process, you are making severe compromises to your data fit to try and improve the quality of the data bars, error bars outside the region. And until you fix that, basically your number one approach is still to do something with Gaussian processes. So I want to pay attention to that type of characteristic as we move forward with the deep GPs. and show that the composite uncertainty in the deep GPs continues to do this. And if I sound slightly frustrated, it's because I am, because this has been known and obvious for the last 20 years, and yet a large section of the community is ignoring these characteristics. I'm not saying that these aren't methods you should pursue and they're not interesting, they are, but please evaluate them correctly. Don't sort of go blindly after trying to reconstruct this piece. Why am I also frustrated about it? Because I went through this in my PhD thesis, basically, because I went through the same process in my PhD thesis, trying to build variational approximations that could capture what a Gaussian process was doing, and I couldn't. And I knew very well why I couldn't, and the reasons are pretty fundamental. They're quite hard to get around, and I think people aren't acknowledging that. Sorry, big rant from me there. Okay. So right, I'm going to skip this to make sure I get onto the, sometimes I would emphasize the way that these models do abstraction, but it's the sort of thing that I care about, but I think the community is caring about a little bit less. So, because I have to be a bit cautious about how fast I click, because everything's going a bit slow. Any questions while I'm clicking away here?
Yeah, just a quick one. I think because we were talking about the error bars, a few people are curious about your opinion on visualizing the marginals. Like, what's your take on it? Because I know Carl has strong opinions, and he talked about that yesterday.
Yeah, no, it's great that he has strong opinions, and I agree with him. Yeah, he's right to have strong opinions, and I'll show you how I'm going to visualize. It's good to have. I think I probably made the error of finding it obvious that there was a problem with visualizing these marginals, so I haven't emphasized it enough in the past. But yeah, it's a big issue, and I'll show you how I sort of try and I think the nice thing with these models is you can skip through very quickly and sample from them. So the sort of thing I try and do to try and pick up on that criticism. And it's definitely something worth working on. I know Carl Henrik's done an amount of work on that, is to put samples through as a sort of, just to remind people, right? Rather than rely on these error bars. Because yeah, totally true. And for a while, it took me a while to realize that that's what people were complaining about. I don't know what's going on here in terms of why it's so slow. I don't seem to be able to get through it either. Come on, it seems to be going in cycles. Okay, I'm just going to not touch it, but I'll stop sharing and talk about, and may end up actually having to restart the slides.
Yeah, just another question. Somebody's curious about what happens if your observations aren't normally distributed? Are these models still?
Yeah, they deal with non-normally distributed observations. Now, that doesn't mean that you should just do Gaussian likelihoods. There's some interesting philosophical stuff that comes up now, and it's sort of a bit there in some of the examples. But yeah, if they're not, sorry, I'm just partially sorting out my slides in the background, so I'll sound slightly distracted while I answer that question. But if they're not normally distributed, yeah, that slide where I'm showing the Gaussian going into the Gaussian process, and then you're getting a non-parametric clustering distribution out on the other side, is kind of highlighting the fact that it's possible to, sorry, the slides are really confused, so I just have to focus on them for a moment. Just restarting the slides. So it's possible for you to come up with very non-Gaussian things, but one challenge with that is that you should still ideally be doing that in your likelihood. If you've got a classification label, don't be going, oh, I can use a deep Gaussian process with a Gaussian likelihood. Well, you can do this. I mean, do what you like, but there's an issue with saying I can use a deep Gaussian process to model the non-Gaussianity of that likelihood, right? Because it's an incredibly powerful way of building non-Gaussian distributions, and you know what your likelihood is, it's classification. So it seems a bit more sensible just to introduce that explicitly rather than rely on the deep GP to handle it for you. Because it's, it makes more sense just to say it's a binomial likelihood. Yeah. other questions? I think it's working again now, so I'll reshare.
I'll let you go on because I'm saving a few questions for the end, so I'll let you do the slides. And
okay. So I'm going to quickly, I think what I'll do in terms of just finishing, so because I do like it when we get lots of questions, etc. Have I shared the right screen?
It's analysis of deep GPs is the slide.
Perfect, yep. Sorry, it doesn't give you great clues, Zoom sometimes. Okay, so there's some nice, I just highlight there's some nice work around from, David knows I hate this title, because it's not a pathology, the thing he talks about. Ironically, those slides we got stuck on, I think those slides, when I showed them in engineering back in 2013, were what inspired, I believe, David to look at what he called a pathology. But it's not a pathology, and I think he would accept that now. It's a property of these processes. But what they really did nicely in this paper is they were able to show that as you drop down the cascade, the derivative distribution of the process. So what do I mean by that? A Gaussian process, the derivatives of a Gaussian process are Gaussian themselves. They're jointly Gaussian distributed with the process. That sort of means they're marginally Gaussian as well, obviously. And that means that when you look at your function, you know, they're quite light tail derivatives. And this immediately tells you don't get discontinuities, right? Because it says, well, the probability of a very large positive or very large negative derivative is very low. But in this analysis, and I think the thing I object to in this paper is they say that this always happens. It doesn't always happen. You have to set parameters correctly for it to happen. They show that under certain parametric assumptions, the derivative distribution of the process will become more heavy-tailed. So as you go through the process, you're going to start getting the possibility of jumps of sort of steep derivatives occurring, which is kind of something you want. So it's not a pathology, it's an advantage. There's another paper which also does some analysis, and this does it from the basis of Markov chain, Mark Dunlop. Another great analysis. Again, be a bit careful because both these papers have simplifying assumptions. And here in this paper, they assume that every layer of the deep GP is using the same structure, the same covariance function, that it's like that the layers are identical. Like, so, you know, the form of the probability distributions, which is interesting because it leads to ability to analyze it, but I've never seen it done in practice. But still interesting. So the thing that they look at is how deep do you have to make one of those models before you've effectively approached a model of infinite depth, which is an interesting question. And the reason they can do that is because they're viewing it as the stationary distribution of a Markov chain, which of course it is. It's the nice thing about these models, that they're a bit more analytic. So I'm going to look a little bit at a couple of data sets now with this formalism to sort of show how it performs, just to finish off. And I'll do it very quickly so we get time for questions. But there's Olympic marathon data, which I like using because it's got these sort of facets here. It's just one-dimensional input, one-dimensional output. And what happened here is the marathon runners got lost. So if you've seen me talk before, I'll often talk about that, how they got lost. So I'm not going to talk about it now. But I like this question. So, Alan Turing was a spectacularly good marathon runner. This is his time listed here. You probably can't make it out. It's 2 hours, 46 minutes in the UK Marathon Championships. Now, that was in 1946. And there's a question there. By the way, I can't run 5 kilometers at that pace. It's just he was extraordinarily, wonderfully fast. I mean, like, to me, mind-blowingly fast. Other people I know probably not so much. So if we do a Gaussian process fit to this data, what I'm interested in here is this year 1946, where there was no marathon run, what's the probability Alan Turing would have won the gold medal? And his time, 3:95, is somewhere up here. So according to this, there's some possibility he would have been the gold medal winning person, because the error bars are showing me that the times could have gone up there. But there's something wrong because this outlier is pulling these error bars up. So it's not handling the outlier correctly. And this relates a bit to that question. We could, of course, put a heavy-tailed noise model in, but we can also fit a deep Gaussian process. And this is the deep Gaussian process fit. So if one Gaussian process is feeding another. And now it's pretty confident that there's some possibility, but it's not within the 95% bounds that Alan Turing would have won the 1946 Olympics. such a nice example, with that time. Because now the error bars are coming much tighter, because actually what's happening here, and this is one of the things I think is very interesting, it's got all this power. It's got massive power to wiggle how it likes, but notice it doesn't overfit. And this is what the model does. It uses uncertainty, and this is the composition of uncertainty that Carl Henrik was talking about last time. So first of all, to the previous point, here's the samples, right? So this is trying to get around. So it turns out that these marginals are pretty good, right? Not that good, because look, we're getting a lot more points below here than we might expect, and the distance of these points. So this is clearly very heavy-tailed, right? The model thinks that there's some possibility that people would run quite fast, which actually makes sense, doesn't it? It also thinks, perhaps incorrectly, that people could go all this fast. But how's it managing to do that? Well, this is the input year, and this is the latent variable Z, which is one-dimensional. So this is like the first layer of the pinball machine. So what it's doing is that is basically linear. So this latent variable it's anti-correlated, right, with year, right? So it's flipping it. It's saying that you're going to go, the latent variable increases. So it's correlated with year. The latent variable increase is going to flip it next time. The latent variable increases with year, but very interestingly, up until about 1980, when the latent variable just flattens off. So it's put some fairly fixed uncertainty in, and then it's mainly straight, but then it flattens off. And then here it's obviously trying to return to the prior, as you would expect. And then this is from that latent variable to the actual pace. So this looks like a tied up version of the curve, doesn't it? This is what the model's done. Very low noise, because this is just the uncertainty in the process. It's not the noise. The noise is low, but what's happening is all those runners from the 80s onwards are being mapped to the same point in the latent variable. So that's how it's causing the flattening out to happen. Now here, what's happening is that the input, so I'm just showing the uncertainty in each layer. I'm not showing the overall uncertainty when I show these. I should have been clear here. But because the input uncertainty in these years here is quite high, that means that the input here uncertainty is high. So things are wiggling around here. And so because the curve is steep, that's leading to a lot of uncertainty in the output. Okay, so pinball, what was the point? Well, here's the pinball plot. This is what's happening in the pinball machine. Basically, in the first row of pins, things are falling almost straight through with some changes, and then until you get to the most recent years when the pins just all fall into the same plot. And then they get bent around the machine like this. I'm also showing, by the way, these uncertainties, which I'm modeling as the ball falls through, which is very reminiscent. I've been doing this for a few years, but of course, it's very reminiscent of the GP Gaussian process flows of, I can't remember the first named author, but Sami Kasky is one of the authors on those very interesting papers, which are like continuous deep Gaussian processes. So the pinball plot here is like a discrete version of the GP flow, which in Gaussian process flow, which these models generally are. I'm going to skip through this example because it's not very interesting, and it's mainly there in case I did one of the intros, which I didn't do this year. And then I'll probably just show 2 example results quickly and then stop because we're over time anyway. So I'm having this step function data. Okay, so here's the step function with the deep GP, right? So this is step function fitted with the Gaussian process. Doesn't like it, doesn't like the discontinuity, thinks the variance is high, everything else. Here's a step function being fitted with a deep GP. Loves it. Now, to the point about error bars earlier, we'll have a look at what's going on here, because it looks, oh, the error bar, no, the error bars are fine if it's 95% confidence intervals and mean, which is how I interpret them. I think it's other people don't interpret them that way. And if you look at them a lot, maybe we should plot them in a different way. But I'm always aware that the underlying distribution could look very different, as it should do in this case. Did that move? As it does in this case. Here's the samples through the system. I think they look gorgeous. So outside the region where it's seen data, what we're seeing, yes, the mean is in here and the variance is high, but what's actually going on is it thinks that the output of the system is either 0 or 1. So with the deep Gaussian process, and we've used 4 layers here, we've managed to get a model which can basically fit non-parametric discontinuity. These points in the middle are pretty much where transitions are happening, right? So it just happens to be hitting transitions, or thinks it might be hitting transitions. Very nice. And then the final example, and just to show you the different layers. So I think Carl Henrik also showed an example of this. It's composing sigmoid-like structures together in order to do that, which makes a lot of sense. And I love the pinball plot. So it's sort of basically, the pinball plot is just pushing things. Like wherever you land, there's some possibility to start in the middle on the input. There's some possibility you could go either way, but it looks a little bit like a Spacer Invader from a 1980s game, which I used to play, so I like it. The final data set, this motorcycle helmet data, which is interesting because it, relating to that question about likelihoods before, it has this heteroscedastic likelihood, and the Gaussian process, deep Gaussian process, can easily handle that. So here with the regular GP, the variance is too high at the beginning. What's going on with this data set? It's a helmet on a rig that is traveling along and then hits an object. So in this bit here, it's got acceleration sensors on it, right? So there's no acceleration because it's moving constantly, but it hits the object. This is the helmet moving back and forth, right? And the noise goes up and everything goes up. So this is the deep GP fit. Okay, doesn't know what's going on here, but we'll see what the samples look like. But yes, it's sort of very flat here. And then there's some underlying thing. Okay, you might worry about these error bars, but let's dig into that by looking at the samples. And you can see actually there's no data up the top here, right? So this stuff is very artifactual, right? Very artifactual. These things are heavily skewed down the bottom. So this is really where what Carl Henrik's saying about these error bars is totally wrong. These error bars, right? They're not actually 95% confidence intervals because they're symmetric, and they shouldn't be symmetric. Yeah, well, I don't know, maybe they should be symmetric. I'll have to come back to that. Let me think about that more. I made a statement without thinking about it. And if we look at what the deep GP is doing underlying, it's doing something very similar to the Olympic case where there's a pseudo-linear function. But here, notice here, the curvy bit is at the beginning, that flat bit at the beginning. So it's using the same trick. It's got these tricks up its sleeve to try and get that flat bit at the beginning, that it's mapping from time a load of points to the same place. And then it's injecting some uncertainty. And then I really like the next, it looks like just like a chirp, a very clean chirp. So this, there's no guarantee that it should do this, but I really like the fact that this looks more like what you might expect in a physics experiment to have happened rather than a dirty real world experiment with a rig and a helmet. It seems to have like this bit cleans up and says, oh, now it's just a physics experiment. And the reason you're getting the skew here is because basically there's input uncertainty on the timing here. So that's how it's modeling that. This input uncertainty is causing this whole chirp to move left and right, which gives it a heavily skewed distribution, which is not apparent in these error bars, right? It's apparent in the samples. It's not apparent in the error bars. And the reason it's skewed is because that chirp is being swung left and right to form all these data points. Okay, I'm going to stop there.
Yeah, Neil, just a quick thing on this example. What are the likelihoods for the data here?
Gaussian, all Gaussian. Yeah, great question. You see, the examples are all in let me just stop sharing. The examples are all in the notebook. You can rerun them. They should run out of the box. There may be little errors because I was fixing big errors this morning, so I may have missed little errors.
There's also a lab as well on it.
And yeah, so you can have a play all Gaussian. When it comes to non-Gaussianity, once I think we'd got this far with the model and you knew you could do it with stochastic variational inference, I think everything becomes possible. And it's just a waiting game for everyone to try all the different combinations. I think the thing that I'm a bit disappointed we're behind on is the quality of software we have for cobbling these things together. We now have like 8 different softwares. Everyone likes to write their own software. I get why, but it's extremely frustrating because what we really need is one piece of software that gives you all these capabilities in the same place, because then we would really make rapid progress about what is useful in real applications, which is, I think, what we're still missing. An understanding of what tricks are useful to deploy in which interesting applications. So I'm going to stop there. My conclusions are that's a deep Gaussian process, and you heard me rant about stuff.
Okay, yeah. So there are kind of two major themes in the question, so I'm going to combine them just for kind of. So a lot of people are asking on the combination of the pros and cons of well, the pros of deep GPs and also neural networks and Bayesian neural networks, and the combination of those. So could you use kernel learning and design aspects of GPs in Bayesian neural networks? And can you use Bayesian neural networks to design kernels for deep GPs or GPs? So kind of those two things.
I mean, you can sort of do anything you like. It's you can do all of that. And I think early on, we've understood you could do all of that early on. And I think what I find very disappointing about a lot of papers that do it is they don't explain why. I mean, you see so many papers where it's like, yeah, so I'm going to do this and put it into that. Okay, that can be done. You know, I can certainly put neural networks into Gaussian processes. I can certainly put kernels into neural networks. It's just composing. Once I accept I can compose these things, then there's some work to do with the, you know, what formalism I'm going to use to do my approximations. I think the thing that I think it's fine. You know, we're in Sheffield virtually, and this is what I claim that these works are. There's a wonderful museum in that image that Will's got up, just up the hill from there. There's a wonderful museum on your way into Sheffield, which shows like pieces of work that come from apprentices of knife making in Sheffield. And they have very intricate metal work on the knives. It's very beautiful, but it's actually a museum of very, very impractical knives, because these were apprentices who were just sort of qualifying for their apprenticeship by doing intricate metal work on a knife that wasn't required to make a practical knife. So I view all those papers as pretty much that. Oh, someone's demonstrated technical capability to make a very impractical knife, and it's an impressive thing, and I'd like to hear a little bit about what troubles they experienced with it. Is it a revolution? No. You know, has it changed the way we think about machine learning? No. What I would really like to see is such intricate metalwork being used to create a practical knife. So, you know, the knives in that museum, you would cut yourself if you tried to cut anything with them. And what I care about is how we deploy in the real world. And what I want to hear when people are doing that is, why are you doing it? And I don't think it's good enough to say, because I can beat this benchmark. But it is good enough, because the whole of NeurIPS has just become an exercise in impractical knives. So apparently that's fine. But it's not good enough for me to be excited about if you don't explain what this gets us that we didn't have before. And I think one of the challenges is it's quite a lot of work to make these impractical knives, as you can imagine. And you don't have enough time to make an impractical knife and think about the type of application you should be deploying your knife for cutting. And that's why we need this sort of more unified tool set, so that we can combine some of these things very easily. And you know, there's efforts in that way. There's Pyro, there's Edward, there's various things, but they don't give us the full flexibility of the Gaussian process that, say, GPy does. So you sort of want something that's a combination of, say, GPy and Pyro, or GPy and, you know, I think GPy cares more about your ability to introduce what you care about in the covariance function than a lot of those toolkits. Sorry, long answer.
Yeah, I'm just interested in time. I'm going to ask one more question. You mentioned GP flows, but a few people are they've seen parallel between the way you introduce deep GPs and normalizing flows. So how do they compare in terms of principle?
Yeah, I think the big difference, I mean, normalizing flows come after deep GPs, but the big difference about normalizing flows is that they're trying to keep the mapping bivariate. So the deep GP doesn't care about that. And also they tend to be deterministic functions being applied to a distribution. So that's also different. But yes, it looks similar in that way. And it's in some sense a shame that a lot of the literature around those things and GANs doesn't know about, say, David Mackay's work on density networks, which is the work that inspires a lot of the things that I've done. Because yes, there's enormous numbers of overlaps. And I think there's great ways of including these things together. But not a lot, and the normalizing flows has some very nice, cool new ideas in it. But yeah, a lot of the core ideas have been around for longer. Yeah.
Cool. Thanks, Neil. That's I wish we could keep going, but I'm aware like people need a few minutes to be able to like stretch your legs. I thought it was amazing. I really enjoyed as well your sort of very emotional kind of like interested emotional. Yeah, exactly. Yeah, getting still what's the word? Excited by things.
Try and get drama about it. Make it a bit more. In the end, I don't really care, but I like to pretend to care for the audience.
No, it's great. Cool. Right. Thanks again for that. Everyone, feel free to ask your questions and stuff on the Hoover app, because like we can discuss this a bit with Carl and Javier in the afternoon session as well in the roundtables. Cool. Thanks again, Neil. I think that's like, I don't know, such a frustration to stop, but we're going to have to stop. Thanks again.
Sorry for overrunning. Yeah, but I think
really
lots of great questions, which was so nice to have in one of these. It's so hard.
No, I know.
Talk to a screen for so long without, and so Will, you did a great job also of introducing the questions, and there's still 177 people out of the max 200 that I saw. So you did a great job of managing to listen in, unless of course you've all got it switched off and are actually
cool. Well, hopefully you've copied the questions somewhere so we can discuss them in the afternoon. Right, we better stop. But I should get some canned applause, but I haven't got that. So just, you can imagine everyone cheering to say thanks. Cool. Thanks again. Yeah.
Thanks everyone for putting it together.
Later, we'll start in 13 minutes with Javier to talk about Bayesian optimization. So